All right. Good morning, everyone, and thank you for joining the multimodal session today. My name is Natasha Earl Young, and I'm the Policy Director for NCDOT, and I'll be facilitating this session. I just want to remind everyone that make sure that your phones are on silent. If you were unable to sign the sign-in sheet, make sure you sign in at the back for PDHs. And if you have any questions, we'll be taking questions after each presentation today. Our first presenter is going to be Sarah O'Brien. Sarah is with the University of North Carolina, Chapel Hill, and she will be presenting on the assessment of separated bike lanes in North Carolina.
Hey, can you guys hear me okay? All right. I'm going to try to use the clicker instead of the laptop. So I'm going to talk to you about a project that we just finished. Actually, we just did the closeout meeting with the Steering and Implementation Committee last week. So this is hot off the presses, although it's not officially published yet. But hopefully this will be some new information for y'all about separated bike lanes and an assessment we did in North Carolina. So for those of you who may not be familiar with what separated bike lanes are, sometimes they're called protected bike lanes or cycle tracks. There's a few different versions shown up here. Basically, they are dedicated bicycle facilities that have horizontal and vertical separation from motor vehicle traffic. So you can see in the top left corner, there's the buffer kind of bike lane with the paint, but you can see the flex posts add that vertical delineation. Going clockwise to the right, you can see a sidewalk level separated bike lane. And so the curb itself provides that vertical barrier. And then the bottom right, we see a separated bike lane where the vehicle parking lane can provide some separation and buffer. And then on the bottom left, we see a bi-directional or a two-way separated bike lane. These are the ones that are sometimes called cycle tracks. So the objectives of our project with NCDOT were these listed here. I'm not going to go into the lit review that we did or findings from the state of the practice review that we did. I'm going to jump right down to the evaluation and some summary information. So when that report is published, you can go back and look at some of those other details. For the evaluation, we collected data and observational studies to understand the application of separated bike lanes in North Carolina. So I'm going to talk about our site selection process, the data that we collected, some hypotheses that we wanted to test based on certain assumptions, and then what we actually found. For site selection, when we did our state of the practice review, we identified some separated bike lanes that were going to be constructed. So there were potentially 8 that we could look at studying through a before-after type of analysis. Ultimately, that was narrowed down to 4 separated bike lanes that would actually kind of work within our project study time period. We had 3 that were in Raleigh, 1 on Crabtree Boulevard, 1 on Lineberry Drive, and 1 on West Morgan Street. And then in Charlotte, we had the Uptown Cycle Link, which actually was running along 3 different roads within Uptown. Ultimately, we also selected 10 sites along those separated bike lanes for data collection. 4 of them were in Raleigh and 6 of them were on the Uptown Cycle Link. So I'm going to walk you through the before and after so that you can understand what changes were made, so that when we talk about the results, you'll start to think about maybe what had impacts. For the Raleigh Crabtree Boulevard location, we picked a site specifically where it intersected with Timber Drive, which is a stop controlled intersection. You can see in the before period that there already was a buffered bike lane along Crabtree Boulevard. And it's a little bit difficult to see in the bottom right, but because of the shading, but they basically put in flex post delineators to create that vertical barrier. And then they marked with a green pavement marking going through the intersection conflict area at this location. On the far side of the street, where you can see that black truck, there's also a driveway that goes into a convenience store, which had a lot of activity. So we were also looking at what was happening at that location and maybe how the change of the roadway could have been influencing behaviors with turning in and out of the driveway. On Lineberry Drive at Trailwoods, that was another stop controlled T intersection. On Lineberry, there was no dedicated bike lane in the before. And then the after, you can see they again put in the vertical delineator with the buffered paint kind of a bike lane. And then using the green pavement markings again, going through the intersection itself. On West Morgan Street, there's not that much that was changed from before and after at this particular site. West Morgan Street already had a buffered bike lane, and so you can see the flex post delineators that were installed in the after. But leading up to the intersection with Salisbury Street, both in the before and after, the dedicated right turn lane for motor vehicles is essentially the predominant movement that's happening there. And so because of space, because of width constraints, the bike lane essentially drops and is merged with the right turn lane to create more of a shared lane type of environment. The pavement marking symbol was not changed to a shared lane or a Shero style marking. They kept the helmeted bicycle symbol with a through arrow specifically for bicyclists that you can see there. I also wanted to point out on Salisbury Street that you can't see it in this picture, there was also a bike lane along Salisbury Street. So the other thing that we were interested in was the interactions potentially with bicyclists who might be turning from Salisbury Street onto Morgan. And on the far side of the intersection of Morgan with Salisbury, on the far side, Morgan Street has the separated bike lane, and I don't believe they put in delineators on the far side. It's just a bike lane. A little bit upstream from that, we actually looked at another segment of Morgan Street where there was a dedicated where there were potential dedicated right turning movements going into the parking deck here, the entrance to the parking deck. So looking more at driveway conflict potential that would change. Again, there was already a bike lane along Morgan Street, a buffered bike lane, and the flex post delineators were installed. You can see there's no green pavement marking or any other changes happening to the conflict area at this location. Now moving on to Charlotte, we can see North McDowell Street, which is the street that the bike lane was going in on. The separated bike lane went in there. That one was a in the before, it had no bike facility. The southern leg of McDowell was a 5-lane cross section plus that center line raised median that you can see in the top left image. In the after, they removed that that median center line and the lanes were narrowed, but it remained with 5 lanes, and they added space for the separated bike lane to go in. You can also see that for the separated bike lane in Charlotte, and this is along the entire Uptown Cycle Link, they have a hardened concrete raised median as the buffering element for both the vertical and horizontal separation. The northern leg of McDowell used to be a 4-lane cross section with 2 through lanes going southbound plus a left turn lane. And in the after, they removed one of the through lanes going southbound. You can also see that they added green pavement markings, not only through the crosswalks or any of the conflict areas, whether they're intersections or driveways, but they also added the solid green pavement markings basically at the entrances or exits, if you will, to the separated bike lane itself to provide more visual enhancement. In this particular site, our camera's field of view was actually not the image that you're seeing here with Google, but it was really so that we could capture changes in behavior based on the change to the southwest corner that you can see in the image here. You might notice there's a corner island right there. So that corner was built somewhat more like a protected intersection style. So we wanted to see the impacts of that. On West 6th Street, so basically the Uptown Cycle Link turns from McDowell and goes up West 6th Street. So we looked at an intersection at North Graham. We actually had 2 camera sites at this location so that we could capture different things that were happening. So in the top left, or sorry, the top row, we've got before and after of the northwest corner. And you can see that there's a busy driveway that's basically just past this this intersection going into a CVS, and you can see the green pavement markings that were added in the after to go through that driveway location. On the bottom row, we're looking at an image showing the southeast going up 6th Street, and we're focused on the space that was originally used as a channelized right turn lane that you can see kind of on the far side of the intersection. That channelized turn lane also had a driveway almost in it that was closed in the after, and the channelized turn lane area of the roadway was basically what was used for the separated bike lane in the after, with a slightly reconstructed median where the channelization occurred. Also, the south of Graham, the 6th Street was originally a 4-lane cross section with a dedicated left and right turn lane, or two dedicated turn lanes. And then it had 2 through lanes, and ultimately that was converted to 3 lanes plus the separated bike lane. North of Graham, 6th Street was originally 2 lanes plus on-street parking, and that parking was removed to create space for the separated bike lane. Another site or intersection location in Charlotte on 5th Street at North Cedar, we also installed as 2 separate sites because we had 2 different camera angles that we're looking at. The top row, we're showing the northwest corner. Again, before at this location, there was no dedicated bike facility. Looking southeast down 5th Street, you can see that it was a 5-lane cross section before, with 2 southbound lanes, 3 northbound lanes, and one of which was the left turn lane that you can see there. And then they had a center line median installed in the before. In the after, there was a 4 cross lane section with 1 southbound lane. So one of the southbound lanes was dropped in the after in order to create space. Also in the before, there was a 5-lane cross section plus parking when you're looking at the bottom row, so the other direction. And then in the after, that was a 4-lane cross section, again, because of that southbound lane being removed. So the reason we had 2 different camera angles here was because we wanted to capture what was happening at the intersection, where you can see the green pavement marking was added to visualize the potential conflict area. But then looking down looking southeast, the bottom images that you see, it's hard to see in this picture, but on the right side, there's actually a driveway entrance to a parking garage going underneath that apartment complex. And so we wanted to look at what was happening along that segment, essentially. And there is green pavement marking, solid green pavement marking going across the driveway conflict. And then our last site in Charlotte was West 5th Street at the I-77 on-ramp. You can see the before image on the left. There was a channelized right turn lane and a bike lane. This was the only location in Charlotte where there was an existing bike lane that was converted to a separated bike lane. The West 5th Street location actually had 2 one-way separated bike lanes or bike lanes on either side of the road. We focused primarily on what was happening with the change at the on-ramp on this location, but I did want to point out that on the far side, that bike lane remained going in the other direction. And they put in it wasn't quite a 2-stage turning location, but they put in a location for bicyclists to essentially queue for using the pedestrian push button to cross 5th Street in order to get to the side of the intersection that you can see here, to get to the separated bike lane, which is a 2-way cycle track style. Let's see, anything else I want to say about this one? And you can see that they, as part of the process, they moved that right turn lane over, and because of the way the median was redesigned there, it creates a narrower turning radius for vehicles that are getting onto the I-77. Okay, so data that we collected, the cameras were left out for approximately 3 weeks in each location. We tried to collect the pre and post data around the same timeframes, but due to pandemic and other issues with the construction timeline for the Uptown Cycle Link, that shifted a bit in Charlotte. And then depending on the site and how much footage we actually had that was usable, we were able to reduce between 9 to 34 days of video per site. We did try to collect the after data at least 1 month after the installation of the separated bike lane. So that's the other reason why Charlotte, they didn't have their official opening of that, I think, until April, I believe, of 2022. Data that we were coding, we counted all the vulnerable road users that were going through the location of interest. We coded interaction types, and there were 4 different codes for that. Could be no interaction, where basically you have a bicyclist or a scooter user or somebody going through and there's no motor vehicles around. Coexistence was essentially meant that we were able to see both a vulnerable road user and a motorist in the general vicinity, but nobody had to change their trajectories in order to negotiate space with one another. An avoidance maneuver was when we saw a change in speed or direction from one of the folks on the road. And then a conflict was basically a more severe avoidance maneuver, something that was like a sudden change, maybe hard braking or swerving that was identified. We also tracked helmet usage and what we called rideshare usage, which was basically the bicyclist or the scooter rider. Were they using some sort of bike share or scooter share like Lime or, you know, whatever. There's a bunch of different ones out there. And then we also looked at whether the bicyclist was riding in some sort of specific cycling gear type of clothing, like a kit or a jersey or something like that. So one of the reasons that we collected the type of data we did is because we had some hypotheses and assumptions about what that meant as a proxy for safety. So we expected that the number of bicyclists traveling along the street would increase after the separated bike lanes were going in. And that was based on the assumption that increase in bicycling activity suggested that people felt safer bicycling because of the separated bike lane being there. We also looked at the percentage of avoidance and interactions, which we expected to decrease once the separated bike lane was installed. For helmet usage, we expected that to increase. And while that might not be directly associated with the installation of the separated bike lane, it's a general indicator of safe riding behavior. And then for looking at the percentage of bicyclists wearing a cycling kit or bike jersey or something like that, we were expecting that percentage to decrease. And the reason behind this was thinking that seeing bicyclists using or wearing those kinds of clothes could be a proxy for them being what we call the strong and fearless typology of a bicyclist, who essentially would be totally comfortable riding with traffic in the road. And that the separated bike lane is more likely to appeal to the interested but concerned type of cyclist that's maybe more of a casual rider and would only feel safe having that separation there. We also looked at the number of vulnerable road users that were using the bike share or scooter share, and we expected that to increase after the separated bike lanes were installed. We expected the number to increase, or the percentage using those shared system vehicles to stay the same or also increase. And again, the idea behind that, the assumption was that people who might be using some sort of micro-mobility ride share service are probably going to be more casual riders who are making short trips, or maybe don't otherwise own a bicycle or scooter, or who are tourists. And so again, the thinking was that they probably represented more of that enthused and confident, or interested in but concerned type of rider. So here's some of our results. Looking at the bike volume, we did see an increase in general in usage, with the exception of the Morgan Street location with the parking deck. You can see we've got the raw before and after data. I mentioned that depending on the site, we reduced a different number of days of video. So we also normalized that data before and after to try to account for that. But even with that normalization, you can see a pretty strong increase in volumes across the sites. Oh, I'm not sure what happened. My screen is blank up here. I was going to go into the interactions next, so hopefully our tech guy can come up and help with that. We looked at interactions both in aggregate as within Charlotte and within Raleigh, as well as across sites. In general, avoidance and conflict maneuvers decreased in kind of across the board. However, it's a little more nuanced in Raleigh, where when you start drilling down to individual sites, we see that maybe not all sites are effectively showing that. And in particular, there were 3 sites in Raleigh where avoidance went up slightly. And there was 1 site, actually the Morgan Street parking deck location, where both avoidance and conflict maneuvers went up. And that was the only site that we saw conflict, percent increase in conflict maneuvers that was statistically significant. So we're not sure really what's going on there, because that was also the location where, the only location where bike volumes decreased. And it looks like I am out of time, so hopefully they can fix the the tech for the next person. Do we have time for questions or? Yeah, okay.
Short amount of time
Yeah.
that you had to really look to see if there was any effects to that. And then my second question is also, once you put in the separated bike lanes, did you start seeing that there were any scooters that were being left parked in those bike lanes as well?
Yeah, so she was asking, did we look at the crash data at all? And then also, did we look at parked scooters in the locations that we were looking at? So with respect to crash data, because our study was before and after, we were looking at very short timeframes. There's really never going to be enough crash data to look at that for bike and ped crashes. You really need at least 3 years, maybe 5 years to be able to do a crash-based study. So no, we did not look at that. And that's why some of the measures that we did look at, we made our assumptions for why we were saying those were potential proxies for safety measures. With respect to the scooter riders or bike share riders, we were only looking at vulnerable road users that were traveling through the conflict points or areas of concern. So we weren't really looking at what was happening on the sidewalk for parked vehicles. So no, we don't have any information on that. But I will say that in general, the usage of bike share and scooter share did increase across the board. And we also saw slight increases in helmet usage. Yeah, so. Okay. Any other questions? I see one in the back. That's you standing there.
Just had to make sure I was the right one here.
You are in the back.
Green pavement marking seems to be a relatively recent thing in NCDOT. Is that something in the last 5 years that has increased?
So NCDOT, I don't think had any standards for pavement markings until recently. There's actually a first phase of a guidance that I think came out, some standard drawings came out in the last year, I believe. So they weren't even out when these agencies were considering installing these separated bike lanes. Most of the agencies that we talked to were looking at either federal guidance that was out there from FHWA, or NACTO has a couple of different design guides. And so that's typically where these agencies were looking to find that design guidance.
I asked that in preparation for a second question. Does the public seem like there's been a bit of a learning curve understanding what green pavement means? I mean, we've typically understood lines and dashes before, but it seems a new one.
Yeah, that is a good question. I don't actually know off the top of my head research around the pavement markings. Do you know, Dan, anything about studies with specific to the green pavement markings? Yeah, so Dan's saying that the green pavement markings that have existed elsewhere outside of North Carolina have gone through the experimental review process. And even though it's not directly part of the MUTCD now, it's generally been accepted and have not, we don't know of specific studies, but as far as we know, there's nothing that shows that they're of concern. One more question and then we probably need to move on.
Okay, I'll try to make it quick. In your report, so this may not be an answer now, will you break out the individual site treatments and their effects? A debate happening in my branch right now is the difference between the buffered bike lanes, and here you had several examples of simply adding that vertical barrier.
Right.
Was that alone enough to cause significant behavior change?
Right. So the closest we got to that was looking in aggregate across the Charlotte sites versus the Raleigh sites, because all of the Charlotte sites were pretty consistent with having that median style separation, and the Raleigh sites tended to have the flex post delineators. And I would say in general, across the board, for all of the measures that we looked at, Charlotte was either more consistent and or had a higher difference in value. Everything, we do show what's statistically significant. Almost all of our results were statistically significant, both at the aggregate and site level. Okay, thanks.
Well, while we work on IT stuff for Zoom, Sarah gave a great presentation. I did make sure that I wrote down some of the questions that we had around education, as well as the other question about the guidance. I'm going to make sure that our IMD unit gets that information. And maybe IMD actually has quarterly update meetings. So if you already haven't registered for those, I recommend that you register for those, and hopefully maybe they could address that through some of their webinars that they'll be having coming up soon. Oh, we're still. Oh, that's the. All right, so I think we are just about there. So we've gotten our people online back with us. So I hope they sticked around and didn't miss too much of the presentation. Next, we're going to have Wesley Kilfer with the UNC Highway Safety Research Center. He's going to be presenting on methods to determine crossing treatments for safer shared use path crossings.
Hello, everyone, and thank you for being here this morning. I am Dr. Wes Cooper with the Highway Safety Research Center, and I'm going to be presenting some findings from a recent NCDOT project that we are actually submitting the final report right now. This project was initially kicked off by Sarah Searcy when she was at ITRI before going to NCDOT. So hi, Sarah, glad to see you here, and happy to share some of the results from this project that you started. So in this project, we were trying to look at shared use path crossings in North Carolina, as we recognize that shared use path crossings, so where you have a rail, or sorry, where you have a trail and you have pedestrians and bicyclists who are coming off that trail and then crossing a paved roadway, we recognize that this is the location that is the most dangerous for those road users, or sorry, for those users along the path of the trail. And in North Carolina, there are some municipal guidelines. There are some crossing treatment guidelines from NCDOT, but there really isn't a lot of sort of broad guidance on the best approaches for treatment for shared use path crossings to be used. During the COVID-19 pandemic, we actually saw a lot of people increase their recreational walking and biking, and there have been increased funds in some locations for wanting to get more people out there and active on our transportation modes. But we also recognize that in the United States, there are a disproportionate number of roadway fatalities that are pedestrians. And so we wanted to think about locations where pedestrians are at risk and come up with an easy set of guidelines that agencies can follow in order to improve safety at these shared use path crossings. It's also important to note that the U.S. Department of Transportation recently endorsed the adoption of what's called a safe system approach. And I'll tell you a little bit more about a safe system approach as I move on. But this was the guiding framework that was proposed to us by NCDOT for how it is that we think about these shared use path crossings. So as we went through this project, we wanted to accomplish several different objectives, and one was to have a safe system informed and practice ready method where you could look at different shared use path crossings, identify the risks at each individual crossing, and then come up with a treatment that both worked functionally to improve comfort, but also would reduce some of those risks and enhance the safety of that crossing location. We also want to provide clear guidance as for the operational geometric conditions in which these different treatment types would be most appropriate. And we also wanted to test and calibrate an evaluation framework. So the framework that we put together for this project is still somewhat theoretical in nature, and we're hoping that future research will build on that. But this is, at least as far as I know, for shared use path crossings, this is the first qualitative evaluation framework of its nature. And then we wanted to provide a set of tools that would be easy to use within Microsoft Excel and could be calibrated to fit local conditions. So we went through a number of different steps in order to fulfill these objectives. We started with identifying where different shared use path crossings are in North Carolina, and then we collected operational data of those by setting up video cameras. We then identified some of the critical interactions between motor vehicle operators and pedestrians and bicyclists at these crossing locations. And then that data fed into a desk review of the crossing locations that we did both through Google Maps and by reviewing some of that video data to make sure that we had the right treatments identified. And that allowed us to fill out a checklist for each crossing that was based on safe system compliance. And then we took those safe system scores that we generated from that checklist, as well as some data collected through the video review. And we ended up developing two statistical models to answer three research questions of: can you predict the time between crossing trajectories of motor vehicle users and pedestrians and bicyclists? And can you predict if conflicts are going to be dangerous, whether or not it would be critical based on a measure called the post-encroachment time? And then we tried to look at what the relationship is between the safe system compliance and the number of interactions at these recorded crossings. And ultimately, this led into a simple matrix that we hope will be useful for practitioners. So I mentioned earlier that we did all this based in the idea of the safe system approach. So the safe system approach is a paradigm or framework that, as I mentioned, has been endorsed by the U.S. Department of Transportation that is supposed to shift us, if we're thinking about safety, from a reactive stance where we look at where crashes have occurred and then try to come up with treatments at those, to instead a proactive stance where we think about where are there risks in the built environments and how can we mitigate those risks now before a crash occurs. So FHWA says that there are 6 key safe system principles that we used when we were thinking about the different criteria for our checklist. And these include that death and serious injury are unacceptable, that humans make mistakes, that humans are vulnerable. That one is especially relevant to pedestrians and bicyclists because you don't have a steel shell to protect you. That responsibility is shared, and we thought about this in the framework of signage and lighting and whether or not there was clear visibility between different road users who are crossing. We also thought about wanting to be proactive in safety and how it's good to have redundancy of different measures if possible. So as I mentioned, we used the safe system framework to try to think about shared use path crossings and to really consider what it is that makes risks at shared use path crossings. So we did a literature review of some of the different safe system based frameworks that are out there. There's one that was developed by VHB called the Safe System for Intersections framework. This is specifically for normal road intersections, but it has some useful information in there about how it is that you can calculate a safe system score. There are also some frameworks that have been proposed by an organization in Australia called AustRoads that look at exposure, likelihood, and severity. And those three terms, those three elements tend to be the way that safe system is conceptualized whenever you're trying to evaluate different sites. So when we think about reducing exposure, this means trying to separate users in space and time. When we think about reducing the likelihood of a severe conflict, this means trying to reduce the motor vehicle speeds where these conflicts occur, as well as making sure that there's good visibility and that there are clear expectations for how different people approaching this intersection are going to use it. And then when we talk about reducing severity, this mostly goes back to that speed element. So speed is involved both in the frequency of crashes and the severity of crashes, but it's also thinking about what kind of mix of traffic you have on a roadway. We know from a study that was done by the Insurance Institute for Highway Safety that as vehicle chassis size has gone up, that has had an impact on the safety for pedestrians in the US. And so this is something we wanted to look at in this project. So we ultimately ended up pulling a larger inventory of 76 sites, and then through a review of the kinds of treatments at these sites, we narrowed down to 16 that we were going to collect our data on. You can see these are across the states. There are some here some in Durham, some in Raleigh and Charlotte, and out in some of the farther reaches of the state as well. These are in suburban, urban, and rural areas. And so we grouped these into 4 common treatment types. There's actually a little bit more nuance than that at each of these sites. We did find at least one that had absolutely no marking whatsoever. They're not supposed to have that. They actually are supposed to have at least some parallel lines across the roadway. But we looked for those ones that have either a standard crossing or no crossing and grouped those into what we call a class 1 or a no treatment. And then all of the sites that had something like a continental treatment, which are those zebra stripes across the road, or a hook and ladder, which is another sort of zebra stripes or larger blocks that sort of look like a ladder going across the road. We grouped those kinds of treatments into pavement markings or class 2. We grouped some of the sites into what we called refuge islands. These are, NCDOT helped us define this clearly, but these are locations that have at least a 6-foot paved median. It was noted in one of our panel meetings with the Steering and Implementation Committee that if it's only an unpainted median, if it's only a painted median, but there's no actual physical infrastructure at that location, then that wouldn't really count as a refuge island. And then the last group would be the class 4. And here's where we combined one site that had an actual traffic signal with several sites that had either rapid flashing rectangular beacons, or RRFBs. I think I got that acronym right. And then hawk signals or pedestrian hybrid beacons, because those all sort of function the same way to create a separation in time for road users. So we looked at these different sites, we grouped them based on the speed limit, or we tried to get a distribution of speed limits, tried to get a distribution of annual average daily traffic, which we got that information from NCDOT's GIS platform. And we also tried to assess what the functional classification of these different roadways are by looking at how the purpose they serve within the network, whether or not it was like a US highway or an NC highway, and however many lanes and speed limits that they had. So here are some images of the different kinds of treatments that you can see. So that class 1, as I said, there were actually some that had nothing out on the roadway. We did actually a visual inspection where we looked in the camera versus what was in Google Maps and in the Google Street View. And we did update a couple sites because they had initially been listed as having no treatment, but one ended up having an RRFB installed. So we did have to update some of our data as we went. You can see that class 2, that is one that does have pavement markings. Class 3 is where you see that refuge island, and then class 4. This is a case where you have what would not be a refuge island because it's not paved there, but you do have a traffic signal that provides some separation in time. And so at each of these sites, we used a similar schema to what Sarah was just talking about. We looked for the kinds of interactions between road users. And we did this by recording up to 48 hours of recordings of crossings at these locations between March and June of 2022. And we examined each of these sites until we were able to get up to 50 shared use path interactions. And so for each of these interactions, we recorded when it occurred, which types of shared use path road users were crossing, as well as if they were platooning. We were really just looking for pedestrians and bicyclists in this location. I don't recall seeing any scooters coded, but it is possible that scooters do use these sites and would also benefit from these kinds of treatments. We looked at the direction of travel, the vehicle size. This was assessed just by saying, is this an SUV or larger? Because we know that SUVs transfer more kinetic energy when they're involved in a crash. And then we looked at if vehicle platooning was happening and if there was an interaction type. So just like Sarah, we coded no interactions, peaceful coexistence, avoidance maneuvers, or severe conflicts. And then we also try to look if there was appropriate behavior since the motor vehicle is at these sites supposed to yield. So we also recorded a measure that's called post-encroachment time, which is just that difference between when the trajectories intersect at a crossing location. And in the literature, we found that post-encroachment time of 1.5 seconds is often used as sort of a critical measure of a dangerous interaction. Now, that isn't always necessarily true. Just because you might have a very low PET doesn't mean that a crash could have happened there. But this was just something that was a test in the literature that was as good a measure as any. And so, as I said, we recorded up to 50 interactions, and we noted how long it took to get up to 50 interactions. Because of the variety in sites that we were looking at, for some of these, it was only a couple hours until we had recorded up to 50 interactions, whereas for other sites, it took several days of coding video data to get up to 50 interactions. So looking at the way that these different data are distributed across the sites, you'll see that there wasn't very good yielding across the state, unfortunately, just very poor yielding at most of our locations. Some sites had over 30% of SUVs or larger vehicles, some had under that. We also tried to normalize the volumes of pedestrians and bicyclists per hour. This was because you would have some peak hours where more people would be crossing, then some off-peak hours where there'd be fewer there. And then we also looked at the total avoidance maneuvers that were observed. So all of that data helped feed into a safe system evaluation framework. As I mentioned, we looked at the literature for what other safe system frameworks exist for evaluating intersections or for evaluating other kinds of facilities. And we tried to group some of the design and operational elements into different buckets of those measures of exposure, likelihood, or severity. And then we had a checklist that a practitioner could fill out just going through a desk review to figure out what ultimately would be like a safe system score. So for each of these elements, the checklist returns a score for like your exposure, a score for your likelihood, a score for your severity, and then it also returns a normalized product of that. And when I say normalized, some of the frameworks, what they do is they actually reduce the score down to 0, 1, 2, 3, or 4 for each of these elements. And so the total score that you could have for a safe system is just 64. And so the higher that number is out of 64, the less compliant that your site is. So it's a little bit counterintuitive. And so looking at the distribution of these safe system scores and the criteria scores for exposure, likelihood, and severity across the sites, as well as what our mean PET was and our number of critical events, some really interesting things started to pop out here. And I'll show some of that on these next few slides. But part of what we really wanted to explore once we had these scores was, can we actually do some regression models that could help us produce some guidance? Like, are there clear relationships between design elements and these safe system elements? And so we tested two different variables. One was after looking at the distribution of data, we realized we didn't really have a normal distribution. So we did just a linear regression model for logarithmic PET. And then we also did a binary logic model for whether or not an interaction was a critical, meaning less than 1.5 seconds. I'm not going to cover the log PET model just because we don't have enough time to get into that. The critical PET was actually very interpretable. We think that it helps us see if something increases the log odds of an interaction being critical or not. And so that's the one I'm going to cover for you. So the main way to interpret, if you're looking at a binary logic model, is to look at the sign of the coefficient. And if it's a positive sign, that means it increases the log odds of whatever your binary outcome is, versus a negative sign, which means that it decreases the log odds of that outcome. In our case, we are modeling the log odds of an interaction being critical, meaning less than 1.5 seconds. And what we found by looking at the treatment type is that compared to traffic control grouping, so that class 4, that all of the other treatment types increase the log odds of an interaction being critical. When we looked at speed limit, we found that the statistically significant speed limits, so 25 and 45 compared to 35 miles per hour, both of those decrease the log odds of an interaction being critical. That 45 miles per hour, sorry, that one wouldn't be statistically significant, but that 25 miles per hour does seem to show that if you have slower speeds, that then you have a decreased log odds of your interaction being critical. We saw that as your AADT goes up, it seems that you have increased log odds of critical interaction. And then the likelihood score and the safe system score, they sort of moved in opposite directions, but likelihood had a much larger coefficient, almost double the other one. So it seems like maybe that's explaining a little bit more about interactions between road users. And here are some distributions for those critical events. And this one actually doesn't really surprise me. We see that the critical events are actually highest in our pavement markings and our refuge islands. They're low at no marking sites. That could just be that these tend to be sites that have lower speeds, and maybe because there aren't good markings there, that pedestrians and bicyclists are a bit more cautious as they approach those sites. But we saw that with traffic control, this also was associated with a fewer number of the number of critical events. And so kind of distilling some guidance from these, we did see again that class 1 through 3 markings, those do seem to have increased their log odds of a critical event. Speed limit matters and AADT matters. And the safe system scores were statistically significant, but a little bit harder to interpret. So as I mentioned, they work in opposite directions, and the likelihood variables are probably important. But there was one thing that really stood out to me as we were doing this analysis, and that was we saw that the sites that had traffic control, so the separation in time, they tended to be sites where your exposure score was highest. And I think the reason for that is that these tended to be sites that had multiple lanes and higher speed limits. And so while you would expect the exposure to be higher, these were also sites that seem to have the best treatments already. So I think honestly, this means that practitioners in NC already recognize that these are sites that need some extra treatment to reduce risks. And so they're already putting good treatments out there. So here are the distributions of these scores. That's that first plot there that shows the exposure score. That talks about that relationship I just mentioned to you, where they tended to be higher at sites that had supplemental yielding or traffic control. For likelihood scores, we did see that likelihood seemed to be highest at sites that had no markings versus the other ones that tended to perform pretty similarly. And then for severity scores, these tended to be the lowest at sites with traffic control and about the same for the other ones. And this, I think, is, again, you had traffic control that was allowing vehicles or providing separation in time and really allowing vehicles or drivers to slow down. And then with the safe system scores, it sort of worked about as we expected, where the refuge islands and the traffic control were working about the same compared to the other two. So ultimately, we produced this matrix. This is still under review for NCDOT, so this isn't a finalized matrix of how you might make decisions on treatment. But the idea is that if you're a practitioner, you can go through and read and say, well, I have less than 6,000 vehicles per day, but I have 2 lanes. So how many, what kind of treatment do I need? Or I have wide lanes or narrow lanes. What kind of treatment do I need? Is there a bicycle lane that is intersecting here? Is there on-street parking? And so we hope that this kind of decision matrix makes things a little bit easier for practitioners to very quickly identify what kind of traffic control or treatment at that crossing that they need. And we actually built this into an Excel tool that can be used to do some scenario testing as well. So we also produced a couple of case studies to help us think through how you might identify problems at a crossing location. So this is the American Tobacco Trail at Wimberley Road, and this is looking at an unmarked site that it's somewhat serving as a two-way collector, and it has a 45 mile per hour speed limit, but otherwise is generally pretty good. There's not a lot of bicycle traffic, but high pet traffic, probably from people using the ATT. There's adequate signage. There are good sight triangles, but not a lot of great lighting. And so if you were to fill out our checklist that we gave you, the only thing that would really stand out is that exposure score, and that's connected to our speed limit. And so if you are trying to think through, okay, how would I go about upgrading this site? Well, you could think about reducing the speed limit, and the checklist would hopefully just point that out to you of, oh, wait, this is a 45-mile-per-hour roadway where people are crossing at an unmarked crosswalk. Or you could keep the 45-mile-per-hour speed limit and maybe say, well, we definitely need some traffic control if we can't change that speed limit. And this would reduce our scores down below the median values for the different classes. So altogether, we combined quantitative video data and qualitative data to provide this framework for thinking about how to identify appropriate treatments for shared use path crossings. We hope that this is valuable for the practitioners. This is still somewhat theoretical, especially that framework. We think that it can be calibrated by NCDOT staff to fit their local contexts. So I do want to thank the co-authors and all the folks who've worked on this project over the last couple of years, and I'm happy to take any questions.
So I have a couple questions.
Okay.
One, the trailheads that you looked at, was
Yes.
the Department of Transportation contacted first before those trailheads were put in?
I'm not sure.
Because a lot of times we find out about trailheads that are installed after the fact.
Right.
And a lot of times, even if we are contacted at, we can always show them better locations to put those trailheads. That'll be much safer if they were to contact the departmental agencies that are going to be impacted. Usually we don't get contacted till well after the fact, until there's a safety issue that's already been noted. The second question or the second comment I have is, they're not necessarily the trail people. I think as part of federal funding should be required to look at their trailheads and look for safe locations. A lot of times they're just buying property cheaply and they're buying it in parts. I'm dealing with one right now in Haw River in Alamance County, where they want to cross a bridge that is not slated to be redone or have any kind of pedestrian facilities. And they didn't take that into consideration when they brought property for the trailhead on one side of the bridge, and then on the opposite side where they could get the property cheaper. So now they're trying to figure out ways in which to get people across the bridge. That's not slated to be rebuilt, but they want pedestrian amenities. I don't know what to do for them in a safe purpose way to get them to cross at that point in time. So I think when they start building these trailheads, if they have federal funds associated with them, that needs to be part of the federal funding as an aspect, is looking at the trailheads as they cross state roads.
Yeah,
Third-
I think that makes sense. And I think with the kind of guidance that we are including in this, hopefully if they are, doing this and have talked to DOT, they can recognize what the operational conditions of that site are and then pick the right thing. But
They don't. I can tell you that right now. I deal with multiple counties, multiple jurisdictional, and they're not looking. They don't come to the Department of Transportation until after they've already bought the property and the trail's already been installed.
well, I would agree with you that that's problematic.
Yeah, yeah. The other concern I have is you're recommending lowering the speed limit and the rule so what my question is going to be is, you said that in lower speed limit areas that you have less conflict. Are those in the municipalities where they're already driving a 25 to 35 mile per hour, or are those in the rural counties? Because a lot of times what's going to happen is I'm going to be asked, they're going to come to me, they're going to see your study, your recommendations. They're going to be like, I want to lower the speed limit. I can lower the speed limit, but is that going to be effective? Are the drivers actually going to drive a lower speed limit? Just because it is posted 25 miles an hour doesn't necessarily mean it's going to be 25 miles, that the driver is going to drive 25 miles per hour. We had a fatality on Church Road in Greensboro where the speed limit was 45. I mean, we did drop the speed limit to 35 for the area, but I can tell you right now that those drivers are not, for that trailhead crossing, for what we did, they're not driving that lower speed limit. And so there's still that problematic speed that's happening for bicyclists and runners crossing the road. So those are that's my added, as a division traffic engineer for NCDOT, my perspective on that.
Yeah, definitely. There isn't necessarily, you're totally right that your operating speed and your speed limit are often not the same thing. And in fact, I think there's a culture around driving above the speed limit. Most of us have that normalized and don't even think about what speed we're going. And here's where I would recommend, if you are someone who is using this framework and you are going out and trying to be proactive, that you would think about ways to collect operational speed data and actually see what's going on. We unfortunately were not able to. We wanted to do that as part of this project. We weren't actually able to collect operating speeds. We were only able to collect some surrogate measures, like is there good yielding behavior, how much complexity are drivers dealing with. But if you recognize that there are speed problems, it may also be worth considering other traffic calming measures that can be implemented alongside the crossing in order to get vehicles to slow down. Because I do recognize that getting people to slow down is a huge challenge. And that's one of our great barriers that we face for pedestrian and bicyclist safety.
I'll ask one more.
Okay.
Are there other crossing situations where this could be useful?
Okay, so we only looked at mid-block crossings as we were doing this, and as was pointed out, these trailheads are often kind of in the middle of nowhere between intersections. There were a couple in Charlotte that were at rail or pretty close to rail locations. We didn't really deal with the rail, especially with this project, because rails are somewhat complicated, but that may be a way to expand this, is to think about locations where you have even more conflicts and more interactions and more complexity because of the rail trail connections there. There are some tools if you were to try to do these at normal 4-leg intersections, but some of these applications could maybe also be considered whenever you're thinking about your 4-leg intersections.
My question probably applied to you and Sarah both, sort of along this line. I know the focus, both your study on bike or passes, but same time you're in this highway environment, highway culture. So question, I know you already answered, you didn't collect the speed, but do you have volume information? The reason I'm asking, I know you collect the video. In that case, you know, people probably argue this is from devil's advocate perspective, like, I know you, some point, especially Sarah's video, you narrow the lanes in order to put the bike lane. In that case, is that reduce the capacity for roadways, for roadway users? Just a thought.
Right. So from a traffic capacity perspective and traffic operations perspective, are you reducing capacity if you reduce the lane width? Right. Yes, that's probably true. I would say there have been studies that show that narrower lanes and more visual friction can correspond to lower speeds. So there may be other benefits from having narrower lanes that offset some of the capacity problems,
Right.
if you're trying to focus on safety.
So that's probably some sort on further studies when you look at safety, but same time efficiency,
Yeah.
when you trying to promote multimodal operations.
Yeah, I would agree with you.
Thanks.
Yeah, I was wondering how you calculated the clearance time or the time between critical maneuvers at multi-stage crossings. Like, I'm pretty familiar with the Woodcroft and ATT crossing. I actually went through there this morning on my way here. And I think everybody else crosses that as two separate streets because of how wide that refuge island is. So if there was a conflict on one leg, would that be considered a conflict even if like the person was like intentionally stopping to cross that second leg, not even looking at traffic going the other way?
Yeah, thanks for asking that question. That's a great clarification that I didn't probably get to in this presentation. So we examined each approach along these roadways separately. And so, yeah, if you have a multi-stage crossing, because you have a refuge island there, we were looking at each crossing event.
Okay, thanks.
Yep.
Hi, it's me again. There is something I've noticed that IMD over at NCDOT has been requiring lately, more increased use of complete streets check sheets as you go with the projects at the onset of the project. I'm sorry, I didn't get your name. Don McPherson here had brought up a really interesting point with respect to municipalities and how they're handling trailheads with NCDOT. And what I was wondering was, this matrix that you've developed here, would there be any thrust upon the municipalities to say, if you're going to be looking at a purchase of a property to make a trailhead, if you're going to be going over a DOT right away, you need to do this first to check to see if it's a good idea.
I would sure hope so.
Okay.
Yes, I would think so.
All right, thank you.
All right, thank you, everyone.
Thank you, Wesley, for that great presentation. Next, we'll have a presentation by Wei Fan with the University of North Carolina at Charlotte. He'll be presenting on analyzing pedestrian industry injuries in pedestrian vehicle crashes using emerging hotspots analysis in XG Boost.
So good morning, everyone. Thank you for coming to the session. My name is Wei Fan. As you can see here, I'm a professor of civil engineering at the UNC Charlotte. So as you can see, lower right-hand corner right there, the first author is one of my former students who graduated from UNC Charlotte with a PhD in INES degree. And he's working right now in University of Milwaukee, Wisconsin and Milwaukee. So this is actually part of his dissertation work. So I will take all the blame, and but all compliments must go to him. And the lower corner, I see Li Song and Xiaojie Liu, two students, also graduated last year. Both took a faculty position in China right now. And this is actually one of the work, piece of work we submitted to the Journal of Transportation Safety and Security. Just got accepted last December. So both students offer a lot of comments and a lot of insights into the model. So credits go to them as well. So the topic of my presentation today is analyzing pedestrian injuries in pedestrian vehicle crashes using emerging hotspot analysis and XG Boost. So as you can see here, so these slides basically talk about one thing about the topic itself. So why this topic is of interest to some researchers and also practitioners in the real world. So as we all know, pedestrians are one of the vulnerable road users. And statistics shows that from year 2008 to 2018, over that 11 years, the pedestrian fatality, then that number increased significantly by 42%. As you can see right there, it's about 1,800 or so additional pedestrian deaths. And then we also, over the same time period, the other traffic deaths actually going down, as you can see. And recent statistic showed that pedestrian and also cyclist, the number going up at a much faster rate than the rest. So that's why this topic is really, really important, not just to us as researchers, but also as the practitioners here. I know Dr. Hammer is sitting there, so of significance to them as well. So this slide talk about the topic itself. And then these slides basically talk about the methodology. So why we use emerging hotspot analysis? Why XG Boost? Why combine them? So there's a purpose here. Okay, as you can see, first block here. So as we all know, the safety, right? All the statistics, it not just stay there forever. The statistic actually changes from time to time, from location to location. So there's no stability in time and space domain, both of them. So that's why we use emerging hotspot analysis to identify the spatial temporal pattern that changes over time and over space. So we want to see whether some locations actually get worse over time And also some location used to be good, but getting worse over time. And, you know, in time-wise, and some maybe used to be good, now getting worse right now, right? Both dimensions could change. So we want to use that tool in ArcGIS. The second, basically talking about XGBoost itself. So why XGBoost? So machine learning obviously is a hot topic, right? In recent years, probably the past 5 years or so, more so than previous years. So XGBoost, as we know, is one type of a boosting method. So compared to a lot of other boosting methods, XGBoost outperform in a lot of areas, in a lot of topics. As if you're interested, you go read the papers. A lot of literature review basically showed XGBoost is the one probably will be widely used by many in the next several years. So the motivation is very clear, right? So we got one hand, we got ArcGIS, the emerging hotspot analysis tool. The other one is we got machine learning techniques. Why not combine them to study pedestrian injury analysis? So that's the purpose here. Now, these slides basically talk about data itself. So we collect the data from NCDOT back and path pedestrian. 2007 to 2018, which is 12-year data. And we have a total of about 17,000 observations over the years. So the background picture, as you can see here, is actually showed the spatial distribution of the pedestrian crashes across the state of North Carolina. And then these slides basically show some basic descriptive statistical analysis here. As you can see, the table and both charts showed the distribution of different injury level. And left-hand side is as an aggregated number over all years. And right-hand side right there is for each and every one of those years from 2007 to 2018. And then these basically give you some ideas about those injuries distribution. So the information could be classified by different groups. For example, by age, by gender, by curved roadway and things like that. So we're getting to the emerging hotspot analysis XGBoost model. As you can see here, the cube here. So this looks, as you can see, X, Y, and Z. X, Y basically represent the spatial domain, which X and Y basically coordinates, right? Location. And Y basically talk about the time domain. So we're trying to figure out using this cube, using this tool to analyze, how the pedestrian injury level changes over the years and over time as well. So these slides, as you can see, for this 12-year data, we used 5,000 by 5,000 feet grid. And we use 1 year as the time slice, but we have 12-year data. Obviously, we have that Z direction, we have 12 units right there. And then we have, we define the neighboring distance to be 20,000 feet. So these slides show basically the 7 different types of spots. And the first 4 of them gonna be the one we're gonna focus. As you can see, the first one is a new hotspot. So just the recent past year, it's become much more significant. And then the second block right there is getting worse over time. And then third block, as you can see, is persistent hotspot. So over the years, it's pretty much stay stable, but it's really one of those hotspots that we need to pay attention to. And then we talk about consecutive hotspot as well. And then diminution and sporadic hotspot and no pattern detected. So we're not going to study them. And then machine learning, basically, as we all know, in this study, we classify into 5 different groups in terms of level of severity, injury severity. So basically, coming from fatality all the way to no injury at all. So 5 different levels. So historically, this is a multi-class classification problem. And typically, the decision tree works really well. And we use XGBoost again, because XGBoost outperforms all other machine learning methods. And then, so a lot of equations here associated with XGBoost, but I'm going to talk about the big pictures only. I'm not going to get into the details here. So the XGBoost basically is a method. So that method can be applied to feed the data. So you typically have a pool of data, right? And you divide the data to training data and also testing data. And then XGBoost basically provide us a framework so that we can strike a perfect balance between minimizing the bias and minimizing variance. As you can see here, the objective is to minimize the total loss. The total loss basically consists of 2 components here. The first component is talking about bias. The bias, which means if you have a training data set, the model can feed the data really well. But we don't want the model to feed the data too well, in a sense that it will bend its rule to just make you happy, right? So that's why we introduced the second term, what we called regularization term. So the regularization term basically trying to minimize the variance, which means, so the purpose is when we feed the data, using the training data set, the model is really good. And then later on, when we apply this model trained by the data set and apply to a new data set, the model will still perform really well. We don't want a model that overfit using the training data set and then perform really bad in the testing data set. So that's the purpose. And then this slide basically talk about one thing, talk about when you branch the trees, right? You have a left and right, and along the way, without branching, so you get gains anytime you branch the tree. So branching tree basically is very simple, the concept. You use some input feature. The feature could be, for example, let's say gender or age, right? Belong to one category, you go to the left, or another category, you go to the right. And the branching, keep branching the trees until you're getting a model and then you evaluate using the training data set, you score them. And later on, you take the average. That's the performance of the model you got. And then later on, you compare them, see which one is the best. So that's the concept here. So along the way, we use a feature importance, which means the total gains in the past of each branch for all contributing factors. So obviously, a lot of features, a lot of variables, those variables could be related to the roadway characteristics, right? The driver or pedestrian characteristics, or the, let's say, day of a week, time of day, and those kind of things. And those are classified as variables. We use as an independent variable traditionally in our discrete choice model. And then whenever we branch the tree, one of the features going to be used. And then there are going to be some gain associated with using that feature to branch the tree, right? You score them. And some may be good. Some other time, that feature may not be good. But on average, some features will outperform others. So that's the concepts here. So we use the model itself can help us rank those features and some may be more important than others. Okay, and then we also use the partial dependence. So partial dependence is similar to the marginal effects. In some of you may be familiar with the discrete choice model, which means you have a factor. For example, it's curved roadway, right? Whether it's curved or not curved. If it's a curved roadway, then you're switching that factor from 0 to 1. And then you can calculate the probability increase if the roadway change from non-curved to curved. You can calculate the probability increase of a fatality, of a disabling injuries or no injuries at all those 5 levels. You can calculate the probability. And then this slide basically talk about some parameters associated with the algorithm itself. So let's use one example as maximum depth. So basically it says the depth of the trees. You don't want that tree to get too large, right? It's too deep. Take a lot of time to calibrate the model. On the other hand, you don't want that tree to be too shallow, so that you may underfeed the data. And then the number of estimator basically talk about the boosting trees. The more trees you have, the better. And then later on, you can take the average and do the forecasting. But you don't want to estimate a lot of trees because we'll take time for each tree, right? So that's why we need to strike a balance. So what we did basically is use randomized search to figure out what's the best combination of all these hyperparameters. So as you can see from these slides, so we rank them, they highlighted in the first row, as you can see there, that's the set of the parameters we use for future studies here. And then the bottom basically shows why the model performs. As you can see, one of the 5-fold cross-validation method, by the way, which means we divide the entire data set into 5 sub-samples. And then we hold one of them for testing purpose. We use the reservoir for training data set. And then we use XGBoost to fit them. As you can see, the accuracy is really good right there. So 94.49 right there. And then we compared XGBoost with traditional discrete choice model. For example, one of them is what we call MNL model. That's multinomial logic model. We also compared with the mixed logic model and also the PBO model as well. As you can see, all these 3 models in traditional discrete choice model, the accuracy actually around 50%. But XGBoost is much, much better, which is more than 90% accuracy. And then these slides basically talk about 3 things here. Left-hand side, as you can see, these are all the input features used along the way until we develop our finalized model. And this figure basically showed the relative importance of all the contributing factors in the model. And the number doesn't mean that much, but it shows, give you some idea, when you compare one variable against the other, okay? And then the middle block, as you can see, this one basically showed the top 15 variables here. And the middle one talked about the average partial dependence, which again means the probability change of switching one variable from 0 to 1. For example, let's use the bottom one as an example here. So right here, you see the pedestrian age less than 25, which means if you switch the right here, if you switch the pedestrian from greater than 25 to less than 25, and then the fatality will actually decrease. So that's what this means here. And then the last block basically showed for fatality and disabling injuries. If one of them is positive, then we select them, which is 9 out of 15. Because our purpose is to focus on the fatality and disabling injuries. Now, this basically gives you a summary of what of the findings here. Okay, so first one, XGBoost, we focused on the 4 different types of hot spots analysis. Use XGBoost, the accuracy is more than 90%. And then 7 factors were identified to contribute to the likelihood of fatal injury, as you can see here. And then for incapacitating injury, there are 5 factors. And then for both fatality and incapacitating injury, we have 3 of them. And then in the future study, we may change, 5,000 feet and also 20,000 feet, those parameters. We may conduct a sensitivity analysis to see how the result might change corresponding to those parameters. And certainly the data, if we have pedestrian and vehicle volume, those data available, that would be great. And we can do something more. Yeah. So that's pretty much my presentation. If you have any questions, I'd be glad to take.
So there is always a gap between research and actual implementation of the countermeasures. What are your recommendations in order to bridge the gap?
Okay, so the question is, there's always a gap between research and implementation. How to bridge the gap?
Correct.
Okay, so to answer your question, I would say education efforts, public outreach activities, and also law enforcement. All this will help. Definitely.
Thank you.
Thank you.
Hi, a few questions actually. I was curious about, did you just use the XGBoost or did you try other algorithms, machine learning? I mean, I disagree when you say it's like XGBoost just randomly outperforms other methods, because I've used like random forest and sometimes it finds itself to be better than XGBoost, and then both have machine learning algorithms. They perform poorly in my set of data than a basic statistical model. And the second question is, did you see the order of variables with the statistical models as well?
Okay, good. Yeah, thank you for the question. So the first question is, why only XGBoost? So because our focus is XGBoost, we can certainly consider comparing XGBoost with other machine learning methods, like you're suggesting. Maybe some like a random forest, right, might outperform XGBoost in some cases, even though some others may not. So one of the future research study, we could compare different algorithms and see how they perform against each other. Yeah, we can do that. That's your first question. The second question is regarding the input features, right? The ranking. So for discrete choice, we did not identify the rankings of all the contributing factors. No. Yeah, we could. But I think the discrete choice model basically give you a model so you can identify the cause and effect, those kind of relationship. But it's very hard to rank them. Some variables may be more important than others when you finalize the model, right? So discrete choice may not have that, mathematically may not, give you that proof. Saying the comparison may be very meaningful. Yeah, I would say it that way. Thank you for your question.
What additional data would you say is needed to improve traffic safety and pedestrian safety overall?
Okay, yeah, thank you for your question. So what additional data you might need to improve pedestrian and traffic injury, right? Safety type of study. So I would say, so traffic volume, like I mentioned in the slides, traffic volume data, maybe pedestrian data, or any crowdsourcing data like Strava, that would help. Yeah.
Some of the important features in your model probably don't have a causal relationship with the outcomes, but are correlations. And I was just wondering what you think they're kind of proxying for. So for instance, like US route, for example, is changing something to be a US route, just putting up the sign probably isn't going to have a causal impact on crash severity.
Yeah, that's a good point. So the XG boost basically, some of the input features, I fully agree with you, may not have the cause and the effects. That kind of a relationship as, we typically have using the traditional model, like a linear regression and discrete choice modeling, those type of models. I fully agree with you. But like using freeway as an example, right? Like a interstate or US route, the one you mentioned. So for example, freeways, the pedestrians should not be allowed to walk on freeways, right? So a lot of research studies show that about 10 states or so, they have law out there that they can be used to deter the pedestrian from entering the freeways. But my student did research, but unfortunately, North Carolina is not one of them. Dr. Hammer, you can correct me if I'm wrong, huh? That's so if you walk on the freeway, yeah, you get a probably much higher risk of sustaining a fatality or disabling injury. Sure. Yeah. Thank you. Thank you all.
So that's the end of this session. Just a reminder to make sure to sign the sheet in the back for PDHs. Thank you.